to tell you something. A Ridiculous Theory of Dark Energy by Nick XIII. We should consider that in the inner world, Brahman is consciousness, and we should consider that in the outer world, Brahman is space. Part 1. The Logic of an Expanding Universe. Infinite and finite models of the universe. What does it mean to say that the entire universe is expanding? The whole universe can only be getting bigger, in any real sense, relative to some other reference frame. Expansion is not a meaningful concept without a reference frame relative to which the expansion occurs. It is common for non-scientists to immediately recognize this problem when they ask, what is the universe expanding into? At the most basic level, there are two scientific models of the universe today, infinite and finite. Both models struggle in their own way to explain the universe's expansion. In infinite models of the universe, the expansion we observe only applies to our portion of infinity. Within this infinite space, there could be millions of other universes, each of them expanding relative to an infinite reference frame. The question, what is the universe expanding into, is therefore not answered so much as it is excused by invoking the speculative concept of infinite space. The conceptual problem of the whole universe getting bigger is absolved of its problematical nature. Even though the whole universe is expanding, it is not getting bigger in any real sense because space is infinite. Finite models of the universe, on the other hand, immediately face the problem of an inconceivable edge of the universe itself. Scientists typically address this problem by hypothesizing a fourth spatial dimension. The analogy of a sphere is often used. A sphere is a three-dimensional shape whose two-dimensional surface has no edge. Finite models propose that the entire known universe is like the surface of a sphere. The three-dimensional universe would have no edge if it formed another type of sphere in a fourth spatial dimension. As the three-dimensional universe expands, its four-dimensional shape would grow in volume in the fourth dimension. But consider what it means to say that the entire universe has a shape. The whole universe can only have a shape, in any real sense, relative to some other reference frame. Shape is not a meaningful concept without a reference frame relative to which the shape takes its form. So, if the universe is shaped like a sphere relative to the fourth spatial dimension, is the fourth dimension infinite, or does the fourth dimension itself have an edge? Ultimately, finite models of the universe can only extend the problem of an edge to another dimension. The question, what is the universe expanding into, is therefore only answered with a temporary stopgap. Finite models of the universe are perpetually undermined by an infinite regress in perspective. In summary, the fact that the universe is expanding destabilizes both infinite and finite models of the universe. It is difficult to overstate the crisis in our theoretical picture of reality. Infinite models can only excuse the universe's expansion as a local phenomenon, while finite models can only push away the inconceivable edge of the universe to another dimension. If a scientist chooses to interpret the expansion of the universe as a simple fact, in other words, if the whole universe is actually getting bigger, it becomes impossible to conceptualize how the universe could be either infinite or finite. This crisis is occurring at the most basic level of our analysis. The only way out, therefore, is to reconsider the basic logic of a universe that expands. The fact that the universe is expanding is actually only half of the fact in question. The other half of the fact, the reference frame relative to which the universe expands, must also be accounted for in order to arrive at any picture of reality that is logically coherent. In short, the fact that the universe is expanding compels us toward a concept of that which is not the universe. The fact that the universe is expanding implies the existence of an entirely different aspect of reality. To better understand this crisis in the structure of our theories, it is helpful to review a recent historical analog. A Brief History of Absolute Space. Writing near the end of his life, Albert Einstein compared and contrasted two distinct concepts of space: space as the positional quality of material objects, and space as the container of all material objects. In case A, Einstein reflected, quote, "Space without a material object is inconceivable," unquote. While in case B, quote, "A material object can only be conceived as existing in space. Space then appears as a reality which in a certain sense is superior to the material world," unquote. According to Einstein, one of Isaac Newton's greatest achievements was to fully and clearly realize that, quote, "Space concept A was not sufficient to serve as the foundation for the inertia principle and the law of motion," unquote. Speaking of this achievement, Einstein continued, quote, "What is essential is that besides observable objects, another thing, which is not perceptible, must be looked upon as real, to enable acceleration or rotation to be looked upon as something real," unquote. Consequently, Newton embraced space concept B, despite reasons to feel uneasy about that decision, which were apparent to both him and his detractors. Quote, "Space is not only introduced as an independent thing apart from material objects, but also is assigned an absolute role in the whole causal structure of the theory. This role is absolute in the sense that space, as an inertial system, acts on all material objects, while these do not, in turn, exert any reaction on space," unquote. This decision was, according to Einstein, not logically inadmissible, although it is unsatisfactory. For its time, Newton's decision was, quote, "the only possible one, and particularly the only fruitful one," unquote. But in the ensuing centuries, problems associated with the concept of absolute space became increasingly acute, which ultimately led to a new concept of space put forward in Einstein's general theory of relativity in 1915. This long history in the development of theory can be summarized as a three-step process, wherein scientists confronted an inconceivable pre-theorized space as the positional quality of material objects, which was then transmuted into an absolute space that acts on material objects but is not acted upon by them, which was finally transmuted into a reciprocal space that both acts on material objects and is acted upon by them. A Problem Resurrected. When Edwin Hubble produced evidence that the universe is expanding in 1929, the recently deceased idea of absolute space was quietly resurrected. Only now that idea was pushed up into a higher level of analysis. The question was no longer about the reference frame for material objects inside the universe, but about the reference frame for the universe itself. Scientists found themselves in a position similar to Newton's. They confronted an inconceivable nothingness outside of the expanding universe, but not to conceive of it was to relinquish any logical understanding of a universe that expands. In the intervening years since 1929, the scientific community has abdicated its responsibility to resolve this catch-22. The following discussion between two astronomy reporters illuminates the prevailing approach to the problem. We get this question all the time. What is the universe expanding into? What's outside the universe? The standard answer is, it's a nonsense question. That's what I thought you were going to say. So, what does that mean? Why is it a nonsense question? To say that there's something outside of the universe, that means that outside of the universe has to exist. We say that all there is of space, all there is of time, everything that is everything is inside of our universe. But if the universe is expanding, then there must be something that it's expanding into. Why can't you just say that everything that is everything is expanding? To summarize, when scientists confronted an inconceivable nothingness outside of the expanding universe, they denied that it was logically necessary to incorporate this nothingness into the structure of our theories, as Newton had done before. As a result, the expanding universe creates a logical conundrum that scientists can only explain by resorting to aphorisms. But while most scientists explicitly reject the idea of a reference frame for the universe, they implicitly embrace this idea in the guises of infinite space and a fourth spatial dimension. In other words, our standard models of the universe quietly rely upon an absolute reference frame for their logical coherence. This reference frame is absolute in the sense that it enables us to conceptualize the entire universe expanding, while the expansion of the universe does not, in turn, exert any reaction on the reference frame itself. This is true for both infinite and finite models of the universe. In the first case, an infinite reference frame enables the expanding universe to be looked upon as something real, but this expansion exerts no effect in turn on the concept of infinity. In the second case, a fourth spatial dimension enables the expanding universe to be looked upon as something real, but this expansion exerts no effect in turn on the fourth spatial dimension. In short, since 1929, scientists have tacitly assigned the concepts of infinite space and a fourth spatial dimension an absolute role in the whole causal structure of our theories, which is not logically inadmissible, although it is unsatisfactory. Review. In any other thought experiment that did not involve the universe as a whole, the assertion that, quote, the universe isn't expanding into anything, it's just expanding, unquote, would be instantly recognized as logically incoherent. For example, the balloon isn't expanding into anything, it's just expanding. Yet it prevailed as scientific wisdom throughout the 20th century, because despite being logically incoherent, this assertion was still mathematically coherent. The expansion of the universe could still be described mathematically without accounting for the reference frame relative to which the expansion occurs. But in the last 20 years, in addition to being logically incoherent, our models of the expanding universe have failed spectacularly on a mathematical level. In order to explain the observed expansion history of the universe, theoretical physicists must admit to neglecting roughly 2/3 of reality, in literal terms, the biggest crisis in the history of science. Furthermore, the most popular guess at how to resolve this crisis, by considering dark energy to be a form of vacuum energy, produces what has been dubbed the worst prediction in the history of physics. The expansion behavior of the universe implies that the density of dark energy in space is 120 orders of magnitude lower than what is predicted by the otherwise successful quantum field theory. And yet this failure to describe the expanding universe mathematically does not seem to have provoked anyone in the scientific community to reconsider the basic logical conundrum at the foundation of our theories, namely, that the expansion of the whole universe is somehow a meaningful concept without accounting for the reference frame relative to which the whole universe expands. Currently, regular people are able to intuit the seriousness of this conundrum, while the scientific community is not. But in defense of the scientific community, the idea of a reference frame for the universe itself is not explicitly conceivable from the contemporary scientific perspective. Science today defines reality exclusively in its objective external aspect, which is another way of saying that reality is defined as an area. The universe is a spatially extended area that contains everything that is everything. It follows that any reference frame outside of this area is ultimately just more area. Properly speaking, there is no outside or reference frame to even imagine. And yet, for almost a century, scientists have employed the speculative concepts of infinite space and a fourth spatial dimension to play the role of de facto reference frames for the universe in the structure of our theories. Infinite space and a fourth spatial dimension play the role of that which is outside the universe, while at the same time they are necessarily interpreted as theoretical features of the universe. By allowing this contradiction to exist at the foundation of our theories, scientists could make the illogical claim that the universe expands relative to itself, or the universe doesn't expand relative to anything, it just expands. In other words, the universe is both infinite and expanding, or the universe is both finite and edgeless. The essential point is that scientists were compelled to account for the universe's reference frame, if only implicitly, because an expanding area is not a meaningful concept without a reference frame relative to which the area expands. This is just a fact of intuitive logic, a fact which remains salient whether the reference frame in question is explicitly conceivable to our imaginations or not. So, for nearly a century, the fact that a reference frame for the universe is inconceivable was held in tension with the fact that it is still logically necessary. The dark energy problem represents the rising of this tension out of our subconscious and into the forefront of our awareness. It represents a lurking philosophical problem suddenly exposed as an acutely scientific one. Our failure to understand the basic logic of a universe that expands developed into our failure to explain the actual expansion history of the universe. The dark energy problem does not represent a failure in the equations of general relativity or a failure to detect an enormous amount of missing energy in the cosmos. Instead, it represents a more basic failure in our theoretical picture of reality, a failure to explicitly account for the reference frame relative to which the universe expands. The development of our theories of space, from Newton to Einstein, can be summarized as a three-step process, wherein scientists confronted an inconceivable, pre-theorized space as the positional quality of material objects, which was then transmuted into an absolute space that acts on material objects but is not acted upon by them, which was finally transmuted into a reciprocal space that both acts on material objects and is acted upon by them. As soon as this process was completed, it restarted on a higher level of analysis. Einstein's general theory of relativity, which concluded the first cycle in our development of theory, created the problems that initiated the second. For the last century, development has stalled between an inconceivable pre-theorized reference frame for the expanding universe and an absolute reference frame that acts on the expanding universe as the foundation of our conceptual system, but is not acted upon by the universe's expansion. To complete this second cycle in our development of theory, the universe's reference frame must be explicitly accounted for. It must be concretized as a fundamental aspect of reality in its own right, as space was once before. Subsequently, the two fundamental aspects of reality, the whole external universe and its reference frame, must be theorized in a reciprocal relationship with each other. To follow through on this process, we should remember that a crisis has occurred at the most basic level of our analysis, that a solution must therefore require a shift in our perspective, and that this transition, being so fundamental, must initially seem ridiculous. But it is also completely obvious. What is essential is that besides the whole external universe, another thing, which is not perceptible, a reference frame for the universe itself, must be looked upon as real, to enable the expansion of the universe to be looked upon as something real. Once a scientist fully and clearly accepts this predicament, it is a short way to realize there is only one available solution. Besides the whole external universe, what aspect of reality can anyone name other than subjectivity itself? Part 2. Theory. Subjectivity, here and now, as reference frame. Subjectivity, or consciousness, the realm of experience, is not an object, which is why it has never been found inside the universe. Scientists have not discovered orbs of subjectivity inside everybody's brains, or halos of consciousness around everybody's heads. Consciousness might therefore appear to be an illusion if it weren't for the fact that it appears this way consciously. In short, subjectivity itself is both undeniably real and not inside the universe. It is a reference frame for the universe, the context in which the whole external universe is manifested. Once we define reality as consisting of two fundamental aspects, the objective aspect, the whole external universe, and the subjective aspect, the reference frame for the universe itself, we can picture reality from either an objective or a subjective viewpoint. Consider objective and subjective views of space-time. From the objective viewpoint, Space-time is a relative coordinate system, an extended field of coordinate points where locations in space, theirs, are also locations in time, thens. But from the subjective viewpoint, every location in space-time is manifested here and now. For example, where is the subjective view of a person in Berkeley, or on the Moon, or in the Andromeda Galaxy? In all cases, here. When was the subjective view of a person 10 years ago, or 1 billion years ago, or 100 years in the future? In all cases, now. From the subjective viewpoint, every different place is here, and every different time is now. It follows that here and now are not features of space-time at all, but rather here and now is a reference frame for space-time itself. Yet science today defines reality only in its objective, external aspect. As a result, the here and now loses its fundamental meaning and becomes merely a descriptive tool for what happens to be my particular there and then. From the current scientific perspective, in other words, space-time is fundamental. Our subjective location within it is merely personal. The scientific crisis that has developed over the last century, of which the dark energy problem is one recent facet, is characterized by the fact that the subjective view of reality, here and now, has a fundamental definition in its own right that has been discounted. Subjectivity, here and now, are synonyms for the non-spatial, non-temporal aspect of reality, the dimensionless dimension, the reference frame for the universe itself. Sharing the universe. As previously discussed, current models of the expanding universe are based on one of two illogical claims: that the universe expands relative to itself, or that the universe doesn't expand relative to anything. In contrast, the following model portrays a universe that expands relative to the observer. To begin to understand the implications of this model, let's consider the situation of this red galaxy. As the universe expands from the perspective of observers in the black galaxy, the red galaxy recedes along a direct line of sight away from them. But as the universe expands relative to observers in the blue and green galaxies, the red galaxy recedes at radically different angles. This creates an obvious problem in the shared universe, an incongruity in the location of the red galaxy. However, since the universe expands relative to every observer in every galaxy, the obvious answer is that the space between every galaxy will expand, and the red galaxy will therefore appear to recede along a direct line of sight away from everyone. Although this is a simple answer, it fails to capture the fundamental structure of this theory. To understand why, consider how the observers in this picture are reduced to features of the whole external universe. In other words, notice how this is only a diagram of space-time. There is no depiction of the non-spatial, non-temporal aspect of reality, the reference frame for the universe itself. There is no depiction of the observer as a universal here and now, only of observers as particular theirs and thens. As a result, this is still a picture of a universe that expands relative to itself, or a universe that doesn't expand relative to anything. In order to resolve this problem and represent this theory accurately, let's imagine instead that every observer has their own personal universe. In this way, we can represent the subjective viewpoint of an observer as the non-spatial, non-temporal aspect of reality, the reference frame for the universe itself. So, for an observer in the black galaxy, the apparent recession of the red galaxy, along a direct line of sight away from them alone, is actually real. As the only observer in their universe, there is no other point of reference relative to which their universe could expand. But the same thing is true in the blue and green universes. The red galaxy actually does recede at radically different angles, depending on the observer. Of course, we are viewing this whole situation from a God's eye point of view. While every observer in this model has their own personal universe, the model itself is a picture of the shared universe. Consider these 5 purple galaxies, all of which are equal distances away from the red galaxy. As time passes and the universe expands, the red galaxy recedes along a direct line of sight away from each of them. After 1 unit of time, the red galaxy appears to be in 5 different locations, depending on the observer. Now let's isolate the situation of the purple galaxy in the middle. As time passes, the location of the red galaxy diffracts into several possible locations in the shared universe. If we could set up a detector in the cosmos and run an experiment from a God's eye point of view, we would see every possible location of the red galaxy hit the detector like a wave. And if we altered the experiment by placing a barrier with 2 slits in front of the red galaxy, its wave of possible locations would hit the detector and split into 2 separate waves, at which point all the possible locations of the red galaxy would interact with each other to produce an interference pattern on the detector. The essential point is fairly simple. In a universe that expands relative to the observer, the existence of more than one observer implies the existence of more than one version of the external universe. If subjectivity here and now is a reference frame for the universe itself, then the cosmos must be visualized as a multitude of personal universes coexisting in the shared universe. Here's another way to think about it. In this diagram, the blue, orange, red, green, and gray galaxies are all exactly on the edge of the black galaxy's horizon distance. Now let's double the age of the universe, assuming, for the sake of clarity, that this universe expands at the speed of light. From the perspective of the blue and gray galaxies represented here, the black galaxy recedes along a direct line of sight away from each of them. When we isolate the perspective of blue's personal universe, the location of the black galaxy diffracts into many possible locations, all of which are on the circumference line of the black galaxy's original horizon distance. As the universe expands from the perspective of the orange, red, and green galaxies, the location of the black galaxy also diffracts into many possible locations, all of which are also on the circumference line of the black galaxy's original horizon distance. In sum, the black galaxy has diffracted outward in every direction. It now exists on the circumference line of its original horizon distance. In effect, the black galaxy now is the circumference line of its original horizon distance. Of course, every other galaxy in this universe has diffracted outward in every direction as well. In 3 dimensions, the possible locations of each galaxy would be represented by overlapping spheres. Dark energy. In 1998, scientists discovered that the expansion of the universe is accelerating, and dark energy was the name given to whatever it is that generates this repulsive effect on the universe as a whole. Since dark energy affects the expansion behavior of the entire cosmos, it appears to be a form of vacuum energy, the underlying energy in space itself. From the moment it was discovered, the leading hypothesis has been that the density of dark energy in space is constant, that the amount of dark energy per unit of space is always the same, from the Big Bang until now. In other words, our standard models of physics and cosmology define dark energy as an intrinsic feature of the universe. Dark energy is a necessary ingredient to explain the observed expansion history of the cosmos, but there is no apparent logic to its own existence, much less its precise value. To put it simply, the standard solution to the dark energy problem amounts to little more than a name, cosmological constant, which acts as a placeholder for a solution yet to come. In the context of the present model, on the other hand, a repulsive effect is generated in the cosmos when each observable universe expands relative to its observer. Dark energy is a natural outcome of different personal universes coexisting in the shared universe. To see how this happens, consider the following series of diagrams. In these diagrams, the galaxies in the background never move, and the space between the galaxies never expands. Their purpose is only to act as a stable ruler for the various observable universes in the foreground, which will grow at the speed of light in this otherwise static cosmos. Note that in these diagrams, as in reality, all observers with the same horizon distance are simultaneous to each other relative to the Big Bang. Accordingly, all of the personal universes in these diagrams can be treated like simple objects interacting with each other in a shared present. Also note that from this point forward, the terms observable universe and personal universe will be used interchangeably, since every observer has their own personal universe in this model. Let's set the horizon distance of this universe to 5 billion light-years, meaning it is 5 billion years after the Big Bang, or about 9 billion years ago. In 2006, researchers using the Hubble Space Telescope detected the earliest evidence of dark energy at this point in the history of the cosmos. Quote, "The stuff we call dark energy was relatively weak, but starting to make its presence felt 9 billion years ago." Unquote. Accordingly, this will serve as the initial starting point for the present model of dark energy. At 5 billion years after the Big Bang, the blue and green galaxies exist right at the edge of Black's observable universe, and Black exists right at the convergence point of the blue and green observable universes. Now let's run the clock forward 1 billion years. At 6 billion years after the Big Bang, everyone's horizon distance is 6 billion light-years. The horizons of the blue and green galaxies now overlap 2 billion light-years at their apex, 1 billion light-years on either side of the black galaxy. Let's also consider the many other galaxies in this universe that were not represented in the previous diagrams. Many of these galaxies will exist along the same circumference line as the blue and green galaxies, all 5 billion light-years away from the black galaxy. At 6 billion years after the Big Bang, every observer that is 5 billion light-years away from the black galaxy will have a horizon distance that extends beyond the black galaxy 1 billion light-years at its apex. If they were all accounted for, their overlapping horizons would form a complete circle around the black galaxy, with a radius of 1 billion light-years. This shaded circle represents a new force of negative pressure in this universe. Negative pressure pulls together, like a stretched-out spring that snaps back in. However, when different regions of negative pressure interact, their inward pulling energies compete with each other, which pulls the space between them in opposite directions and generates a repulsive effect. According to the cosmological constant hypothesis, negative pressure is simply intrinsic to the energy in space itself. In the present model, on the other hand, negative pressure is generated by the fact that each observable universe expands relative to its observer. When two personal universes overlap and expand in opposite directions, they push against each other in the shared universe, which creates a region of negative pressure in between them. And since different observable universes, centered on different galaxies, are overlapping everywhere, a repulsive force is evenly spread across the entire cosmos. Notice how dark energy is represented as a direct function of the horizon distance in this model. Accordingly, this shaded circle represents the total dark energy content of this universe. If residents of the black galaxy looked into the sky at this moment, they would see the universe expanding for 5 billion years governed by the law of gravity, followed by 1 billion years when a new source of negative pressure produced an additional expanding effect. Dark energy has influenced the expansion behavior of this universe for 1 billion out of 6 billion years. The total dark energy content of this universe is therefore 1/6, or 17%. Understanding the point of transition. Uncertainties in the universe's current rate of expansion, known as the Hubble constant, as well as a general lack of data, make scientific projections about the expansion history of the universe somewhat variable. However, it is clear that at some point around 9 or 10 billion years after the Big Bang, 4 or 5 billion years ago, the expanding force of dark energy overtook the contracting force of gravity as the dominant force in the universe, and the expansion of the universe re-accelerated. Scientists are now in the process of compiling a precise history of the expanding universe, which, among other things, will establish an exact date for this critical point of transition, when dark energy exceeded 50% of the total energy density in the universe. With this in mind, let's run the clock forward in our model of the universe. It is now 7 billion years after the Big Bang, and everyone's horizon distance is 7 billion light-years. The shaded circle around the black galaxy has therefore grown to a radius of 2 billion light-years. Dark energy has influenced the expansion behavior of this universe for 2 billion out of 7 billion years, meaning it has grown to 2/7 or 29% of the total energy content of this universe. In addition to representing an increased percentage of the universe's total energy content, this larger shaded circle also represents an increase in the strength of dark energy itself. To understand why, think of the dotted circle as the imaginary boundary of the shared universe. As personal universes expand and overlap with each other, more space is squeezed into the shared universe, and therefore, more pressure is placed on the shared universe to expand. Kind of like a large balloon that is filled with a bunch of smaller, expanding balloons, more pressure is placed on the large balloon itself to expand. Now let's fast forward to 10 billion years after the Big Bang. At this point, it has been 5 billion years since dark energy started to make its presence felt in the cosmos, half the age of the universe itself. If residents of the black galaxy looked into the sky at this moment, they would see the universe expanding for 5 billion years governed by the law of gravity, followed by 5 billion years when a new source of negative pressure produced an additional expanding effect. In short, 50% of the total energy content of this universe is now dark energy. The essential point is that, in this model, the expanding force of dark energy has overtaken the contracting force of gravity at a point in cosmic history that aligns with real-world observations. Furthermore, in this model, the strength of dark energy itself has continued to grow since its emergence 5 billion years ago. However, from this point forward, the strength of dark energy will decline. The point of transition, when dark energy overtakes gravity as the dominant force in the universe, is also the peak of negative pressure in the universe. To understand why, let's consider how this universe looks a couple of billion years after the point of transition. It is now 12 billion years after the Big Bang, and it has been 7 billion years since we began tracking the growth of dark energy. The shaded circle around the black galaxy has therefore grown to a diameter of 14 billion light-years. Notice that, for the first time, this distance is longer than the horizon distance of the universe itself. In order to appreciate the consequences of this development, let's directly compare this region of negative pressure to the cosmic horizon distance. Remember that negative pressure functions by pulling regions of space together. When these inward pulling regions of space interact with each other, they pull the space between them in opposite directions, which generates a repulsive force that pushes the universe apart. But at this point in the history of the cosmos, the regions of space being pulled together are larger than the horizon distance of the universe itself. As a result, each region of negative pressure now works to shrink the distance between an observer and their cosmic horizon. In other words, the competition between these inward pulling regions of space, which used to generate a repulsive effect on the cosmos, has reached its limit, and the strength of dark energy itself is now declining. Here's another way to think about it. At 10 billion years after the Big Bang, the negative pressure that can be generated between the blue and green universes reached its limit, even as their horizons continued to expand and overlap. After this point of transition, the blue and green universes were not just pushing against each other anymore, they were also pushing through each other. As a result, there was a release of negative pressure in between them, and the repulsive force of dark energy declined. At the same time, there was a release of new space into the shared universe, causing its expansion to accelerate. Up until the point of transition, personal universes had been overlapping with each other for 5 billion years, squeezing more space into the shared universe, putting more pressure on the shared universe to expand. At 10 billion years after the Big Bang, there was simply no more room for personal universes to squeeze together without finally pushing through each other, and therefore pushing the shared universe apart. Here's a third way to think about it. Remember that if every observable universe expands relative to its observer, then every galaxy will diffract into many possible locations in the shared universe. We began tracking this process at the earliest observed evidence of dark energy, roughly 5 billion years after the Big Bang. At the point of transition, 10 billion years after the Big Bang, the black galaxy has diffracted outward in every direction for 5 billion years. The possible locations of the black galaxy therefore exist on a circumference line with a diameter of 10 billion light-years. Notice how this distance is equal to the length that every photon in the universe has traveled since the Big Bang. At 12 billion years after the Big Bang, the black galaxy has diffracted outward in every direction for 7 billion years. The possible locations of the black galaxy therefore exist on a circumference line with a diameter of 14 billion light-years, which is longer than every photon in the universe has traveled since the Big Bang. In other words, the black galaxy now exists outside of the universe itself. For the last 2 billion years, the light that has reached the observers in this galaxy simply had nowhere to come from. It was light from beyond the edge of all reality. To put it simply, at 10 billion years after the Big Bang, observers threatened to see deeper than the universe was large. The expansion of the universe accelerated at this juncture because it had to. Toward a precise history of the expanding universe. Let's run this model forward to the present. It is now 13.8 billion years after the Big Bang. The earliest observed evidence of dark energy was about 9 billion years ago, or 4.8 billion years after the Big Bang. Now let's calculate how much dark energy is represented in this picture and compare it to real-world observations. In itself, the proximity of these two figures is a promising congruence for the idea that dark energy is a direct function of the horizon distance. When analyzing the dark energy problem, the fact that the time between the earliest evidence of dark energy and today, as a fraction of the universe's age, is so close to the current dark energy content of the universe is a coincidence that seems to have rarely, if ever, been recognized and needs to be explained. Although this coincidence is anticipated and explained within the framework of the present model, the slight difference between these two figures still needs to be accounted for in this context. Since there is nothing to do but wait for new data from new telescopes to refine our observations of the cosmos, there is nothing to do but accept the earliest observed evidence of dark energy at roughly 9 billion years ago. That leaves the age of the universe as the only other variable to adjust in order to shrink the difference between these two figures. And, as it happens, a recent measurement discrepancy in the Hubble constant implies that the universe might not be 13.8 billion years old. There are two main ways to measure the universe's current rate of expansion. The first, most simple and direct way is to measure the light from supernovas or quasars in relatively nearby galaxies. This method reveals an expansion rate of about 73.5 kilometers per second per megaparsec. The second way is to analyze the cosmic microwave background, the earliest visible light in the universe, emitted roughly 380,000 years after the Big Bang, and deduce the current expansion rate of the universe based on that data. In order to make this deduction, scientists assume that the expansion behavior of the universe is driven by a cosmological constant, that the density and strength of dark energy per unit of space is always the same, from the Big Bang until now. This method yields a slower expansion rate of 67 kilometers per second per megaparsec. These two methods have lately become so precise that the discrepancy between them cannot plausibly be attributed to measurement errors. As a result, this discrepancy represents a new and glaring problem for the cosmological constant, a direct observational contradiction of the hypothesis. Quote, "It's as though you predicted how tall a child would become from a growth chart, and then found the adult he or she became greatly exceeded the prediction." Unquote. In the ongoing debate over this discrepancy, the present model is strongly aligned against the slower value for the Hubble constant of 67 kilometers per second per megaparsec. Again, scientists deduce this value by assuming that dark energy itself is unchanging, that the force of dark energy is mysteriously intrinsic to the nature of reality. In contrast, this model views dark energy as a force that is generated by physical processes and varies in strength over time. It therefore sides with the faster value for the Hubble constant of 73.5 kilometers per second per megaparsec, which already has the major advantage of being derived from direct observations of light in the contemporary universe. If the Hubble constant is 73.5 kilometers per second per megaparsec, then the universe is almost precisely 13 billion years old. With this new figure, we can use the relationship between the age of the universe and its dark energy content to reverse calculate the date when dark energy started to make its presence felt in the cosmos. And, according to this model, the expansion of the universe accelerates at double the time of the initial growth in dark energy. Finally, we can graph this predicted expansion history of the universe like this. Another coincidence problem. Looking back at the history of this universe, it appears to be nearly divided into thirds. The initial growth in dark energy occurred 4.1 billion years after the Big Bang. The expansion of the universe re-accelerated after another 4.1 billion years, and that was 4.8 billion years ago. This new coincidence problem could become more glaring if there was only a slight reduction in our estimation of the dark energy content of the universe, which has already been declining in recent years, from roughly 73% a decade ago to roughly 68% today. If scientific estimates of this value decrease another percentage point or so, then, according to this model, the expansion history of the universe will be divided into thirds, and we will find ourselves existing right at the end of the last third. This would imply a new intracyclic model of cosmology, with phase changes at intervals of roughly 4.33 billion years. To see if this is plausible, let's consider a fourth way to visualize the fluctuations in the strength of dark energy over time. Again, when the blue and green universes push against each other, they generate negative pressure in between them, which exerts a repulsive effect on black's universe. However, when they push through each other, the strength of that repulsive effect begins to decline. This allows the gravity, positive pressure, of black's universe to strengthen once again. In the present diagram, this shift in the pressure balance of the cosmos is represented by a new circle of positive pressure that grows into and offsets the old circle of negative pressure. As the blue and green universes continue to push through each other, the new circle of positive pressure will eventually offset the old circle of negative pressure completely. At this point, the attractive force of gravity will overtake the repulsive force of dark energy, and the expansion of the universe will decelerate once again. Immediately after this point, in an intracyclic model of cosmology, negative pressure would begin to be regenerated. A new circle of negative pressure would grow into and offset the old circle of positive pressure. In short, we would be back to where we started at the initial growth in dark energy. Here's another way to picture it. We can think of the pressure balance of the universe as a dynamic interplay between its positive and negative components. In this diagram, the red line represents the universe's positive pressure component, while the purple line represents its negative pressure component. The relative strength of each component is measured on the y-axis, and time is on the x-axis. Initially, the negative pressure component of the universe is dominant, and the expansion of the universe is accelerating. The shaded area under the curve represents all of the pressure being generated in the universe. So, to the left of the dotted line, most of the pressure being generated in the cosmos is negative, while to the right of the dotted line, more positive pressure is being generated than negative. However, the total pressure content of the universe, the total area under the curve, remains mostly negative, more purple than red, until the following line is crossed. At which point, there is a phase shift in the cosmos. The total pressure content of the universe becomes mostly positive, and the expansion of the universe decelerates. The cycle then repeats itself, with positive and negative components in opposite places. In short, when the cosmos is in its accelerating phase of expansion, it gradually generates positive pressure, an attractive force that eventually pulls the universe into a phase of decelerating expansion. Then, in its decelerating phase, the cosmos gradually generates negative pressure, a repulsive force that eventually pushes the universe into a phase of accelerating expansion. With this in mind, let's look back at the history of the universe once again, given our most current knowledge. At present, it is 13 billion years after the Big Bang, and dark energy accounts for 68% of the universe's energy content. Given these figures, according to this model, the universe undergoes phase changes at intervals of roughly 4.1 billion years. The universe first accelerated, then decelerated, then re-accelerated, and 700 million years ago, the universe entered into a new decelerating phase. Of course, this is not what actually happened. Observations indicate that the expansion of the universe is still accelerating. Therefore, as previously mentioned, in order for this intracyclic model of cosmology to fit with observations, our current estimates of dark energy must be slightly high. The biggest share of the universe's energy content that dark energy could account for is 66.66%, which would place us right at the end of a third cycle in the history of the cosmos, where each cycle is roughly 4.33 billion years long. Finally, there is an unnerving aspect of this new coincidence problem that is difficult to dismiss. The present model bears a striking resemblance to one feature in particular of Hindu cosmology, the notion of a kalpa, which is the Sanskrit word for eon, or vast period of time. In Hinduism, a kalpa is equal to 4.32 billion years. This constitutes a day of Brahma, which is followed by a night of Brahma. Brahma, Sanskrit meaning swelling or expansion, is, quote, God and his manifestation as creator of the universe, unquote. At the end of Brahma's daytime period, the world is annihilated, and the universe itself enters into a cosmic winter. Nighttime, another 4.32 billion years, is an age of dormancy until creation is renewed the following day. Dark matter. Scientists have known for almost a century that there is not enough ordinary matter in spiral galaxies to account for their high rotation speeds. Dark matter was the name given to whatever it is that generates the missing gravity needed for spiral galaxies to hold themselves together as they rotate. Of course, dark matter is dark, in other words, nowhere to be found. It does not interact with ordinary matter except through its gravitational effect. Moreover, unlike ordinary matter, dark matter is collisionless. When two regions of dark matter pass through each other, the dark matter does not interact with itself. While the conventional assumption remains that dark matter is a particle, other ideas have been developed, some of which attempt to unify dark matter and dark energy into a single phenomenon. One of these ideas is that a fluid with negative mass permeates the cosmos. Recall that the cosmological constant hypothesis defines dark energy as an intrinsic property of space itself, meaning the amount of dark energy per unit of space is always the same. Therefore, when more space is created as the universe expands, more dark energy is also created, and, as a result, its repulsive effect on the cosmos increases over time. In contrast, quote, negative mass particles would become more spread out as the universe expands, meaning that their repulsive effect would become weaker over time, unquote. This behavior would not explain the actual expansion history of the universe, which has previously led scientists to abandon this idea. If a dark fluid does in fact exist, it should not thin out over time. In order to resolve this problem, a new dark fluid model proposes that negative masses are continuously created. If negative masses continuously burst into existence, then dark fluid would not dilute as the universe expands. This model could therefore explain the expansion history of the universe just as well as a negative pressure component intrinsic in the fabric of space. Unfortunately, in the same vein as the cosmological constant hypothesis, the dark fluid model offers no reason for why and no explanation for how negative masses continuously burst into existence, other than the fact that it is necessary to explain the observed expansion history of the universe. Nevertheless, the dark fluid model is still superior to the cosmological constant hypothesis in that it also offers an explanation for dark matter. Negative masses are, quote, a hypothetical form of matter that would have a type of negative gravity, repelling all other material around them, unquote. If you pushed a negative mass, it would accelerate towards you rather than away from you. In the dark fluid picture of reality, quote, the gravity from the positive mass galaxy attracts negative masses from all directions, unquote. As the dark fluid comes nearer to the galaxy, it exerts a stronger repulsive force onto the galaxy, which allows it to spin at higher speeds without flying apart. The essential point is that, quote, the surrounding repulsive force of dark fluid can also hold a galaxy together, unquote. As the author concludes, quote, the outcome seems rather beautiful. Dark energy and dark matter can be unified into a single substance, with both effects being simply explainable as positive mass matter surfing on a sea of negative masses, unquote. In the context of the present model, the dark fluid idea is clearly pertinent. In this context, negative masses are a direct analog to different personal universes coexisting in the shared universe. When different personal universes push each other, overlap and expand in opposite directions, they accelerate towards each other rather than away from each other, just like hypothetical negative masses. As previously discussed, in the universe's accelerating phase of expansion, positive pressure is gradually generated in the negative pressure-dominated environment. Therefore, as each observable universe expands relative to its observer, positive pressure is generated around each galaxy, which attracts the negative pressure environment from all directions. In a way that is directly analogous to the dark fluid model, a repulsive force is exerted back onto the black galaxy from every direction, which amounts to an extra gravitational effect in the region around the galaxy, a halo of phantom gravity that holds the black galaxy together. On the other hand, in the universe's decelerating phase of expansion, negative pressure is gradually generated in the positive pressure-dominated environment. In this case, as each observable universe expands relative to its observer, the negative pressure generated around each galaxy attracts the positive pressure environment from all directions. Although these interactions are contrasting, the result is the same. An attractive force is exerted back onto the black galaxy from every direction, an extra gravitational effect that keeps the galaxy intact. In short, no matter what phase the universe is in, galaxies are held together by the pressure cycle of the cosmos, the ongoing interplay between attractive and repulsive forces in space. The outcome seems quite beautiful. Dark energy and dark matter can be unified into a single theoretical framework, where both effects are simply explained as the result of personal universes rippling outward in the ocean of the shared universe. In addition, the present model offers an explanation for certain qualities of dark matter that otherwise remain mysterious, namely, where and when dark matter appears or does not appear in the cosmos. Most galaxies have the same basic distribution of dark matter to ordinary matter, roughly 5:1. However, scientists have now discovered a few anomalous galaxies that appear to have either no dark matter or, conversely, seem to be almost entirely made of dark matter. In both cases, these are ultra-diffuse galaxies, non-spiral collections of stars that are often as large as the Milky Way, but only shine 1% as brightly. In short, although dark matter is an extremely common component of galaxies in the universe, and a guaranteed component of all spiral galaxies, it also has the anomalous quality of being something that a galaxy either possesses or does not possess in certain instances. But these anomalies are straightforwardly explained in the context of the present model. In a universe that expands relative to the observer, a galaxy with no dark matter indicates a region of the cosmos with no observers. Since no personal universe is centered on this ultra-diffuse galaxy, there is no force expanding outward from that locus to counteract the pressure in the shared universe. As a result, no dark matter is generated around this galaxy, which is a kind of cosmic wasteland where the subjective aspect of reality, the reference frame relative to which the whole external universe expands, is apparently not manifested. Of course, this raises the question of what it means to say that consciousness is either manifested or not manifested at a particular location. In our standard models of physics and cosmology, physical systems evolve and complexify to the point where they cross a threshold, the nature of which remains an open question, into coherent sentient life forms. In the context of the present model, this open question simply remains an open question. However, it is restated in different terms and has different implications. In this model, the question is, at what point does the indeterminate shared universe collapse into a concrete personal universe? In other words, at what point in its evolution does a physical system trigger the wave function collapse of space-time itself? At the evolution of cells, eyes, telescopes? Whatever the case may be, the essential point is that a galaxy with dark matter is a place where subjective experience happens. A galaxy that appears to be practically all dark matter, relative to its ordinary matter content, indicates a region of the cosmos where observers must be present. A personal universe is expanding outward relative to this galaxy, which counteracts the pressure in the shared universe and generates the extra-gravitational effect of dark matter. This ultra-diffuse galaxy is a locus of sentient life, a point of reference relative to which the indeterminate shared universe has collapsed into a concrete personal universe. Finally, notice how this model straightforwardly explains the observed behavior of dark matter in colliding galaxy clusters. When two galaxy clusters pass through each other, the individual galaxies in each of them are unlikely to collide. However, the bulk of ordinary matter in a typical galaxy cluster is actually found between the galaxies in the form of diffuse gas, and this gas is bound to collide when different galaxy clusters pass through each other. In this composite image of the bullet cluster, which is actually two clusters that have recently passed through each other, the galaxies are highlighted in blue while the gas is highlighted in pink. During this collision, the gas between the galaxies of each respective cluster was displaced. It now floats in between the two clusters themselves. Since the bulk of ordinary matter is found in the gas, that should also be the place where gravity is the strongest. But this is not what we observe. The force of gravity is not displaced along with the gas. Instead, it remains centered on the galaxies themselves. Since no personal universe is centered on the cloud of gas, there is no force expanding outward from that region to counteract the pressure in the shared universe. As a result, most of the gravity is still generated around the clusters, which are loci of sentient life, points of reference relative to which the indeterminate shared universe collapses into concrete personal universes. Matter-Antimatter asymmetry. Another one of the major problems generated by our standard models of physics and cosmology is the current asymmetry between matter and antimatter in the universe. The Big Bang should have created these two types of matter with opposite charges in equal amounts, but today, everything we see is made almost entirely of matter. Large, stable quantities of antimatter do not seem to exist at this time in the cosmos. This problem is compounded by the fact that matter and antimatter particles annihilate one another when they meet, converting into pure energy. It therefore seems as if matter and antimatter should have destroyed each other right at the beginning, and the Big Bang should have produced a universe with nothing but leftover energy. In short, according to our best principles, the material universe should not exist. The conventional explanation for why the universe does in fact exist is that some physical process took place during the first split second after the Big Bang that favored matter over antimatter, and this led to the otherwise unexpected surplus of matter that we have today. For decades, scientists have searched for tiny differences between matter and antimatter, which could help explain the universe's minuscule but highly consequential favoritism for matter. Recently, this already strained hypothesis became less probable. In 2017, the magnetic properties of the antiproton were measured with as yet unparalleled precision. Scientists then compared these figures to the magnetic properties of the proton and found no discrepancy between the two types of matter. Quote, "All of our observations find a complete symmetry between matter and antimatter, which is why the universe should not actually exist. An asymmetry must exist somewhere, but we simply do not understand where the difference is." Unquote. If we accept what appears to be true, that the matter-antimatter asymmetry in the universe is not a result of slight differences in the structure of matter versus antimatter, then only two other explanations for this asymmetry come to mind. The matter-antimatter content of the universe is asymmetrical across space, or the matter-antimatter content of the universe is asymmetrical across time. The first hypothesis has been widely considered. Perhaps other regions of the cosmos, beyond our observable universe, are predominantly composed of antimatter. In this event, scientists are faced with the problem of, quote, coming up with a mechanism that, shortly after the Big Bang, would have separated these now gigantic clumps of antimatter from the neighboring clumps of matter. However, no such mechanism has yet been envisioned. Unquote. Clusters of matter and antimatter need to be separated from each other to prevent their mutual annihilation, which converts their mass into gamma rays. If certain galaxy clusters within our observable universe were made of antimatter, quote, then there would be immense gamma radiation coming from the boundary regions between clusters of different types. At present, such radiation is not observed, a fact that again argues against this separation of matter and antimatter across space. Unquote. That leaves the final explanation, that matter and antimatter are separated across time. It appears this hypothesis has never been seriously considered, and this is, undoubtedly, because a basic shift in perspective is needed to even imagine it as a reasonable possibility. Given our standard interpretation of Big Bang cosmology, this hypothesis is inconceivable. Under this interpretation, the universe materialized from an implicitly evident but explicitly unaccounted for nothingness. This nothingness was, quote-unquote, before the Big Bang, and has absolutely no connection to the material universe from the Big Bang onward. To put it simply, the universe materialized as a one-time creative event, after which the creation was fully created. The universe was fully non-existent, and then, after the Big Bang, it was fully existent. All of the matter and antimatter that was created by the Big Bang should therefore be present inside the universe all at once, at any given time during its existence. But let's consider the fact that the Big Bang itself is not a space-time event. The Big Bang, if we want to consider it as a thing in itself, is both inside and outside of the universe. It is both a space-time event and a non-spatial, non-temporal, quote-unquote, event. Our standard interpretation of Big Bang cosmology only highlights half of this equation, the half that is inside the universe after the Big Bang occurred. In the present model, on the other hand, both inside and outside the universe are accounted for as fundamental aspects of reality in their own right. These two aspects of reality, the whole external universe and its reference frame, maintain a relationship with each other, rather than breaking apart the moment after the Big Bang. In this conceptual framework, the universe is never fully existent or fully non-existent. Instead of an escape from non-existence, the history of the cosmos unfolds on the backdrop of non-existence. In this view, rather than a simple moment of creation, the Big Bang represents the fullness of creation. The fact that every different place and every different time in the history of the cosmos is also, from the subjective viewpoint, here and now, a union between the entire history of space-time and the non-spatial, non-temporal aspect of reality, an infinite and eternal singularity. Under this new interpretation of Big Bang cosmology, the equal amounts of matter and antimatter that are manifested in the Big Bang do not need to be present all at once at any given time in the history of the cosmos. So long as, in the fullness of time, the matter and antimatter content of the universe is equal, the universe might undergo phases when it is composed of matter or antimatter almost exclusively. Furthermore, in this view, the perfect cancellation of matter and antimatter in the Big Bang, which is predicted by our standard models of physics and cosmology, but is also inconceivable in this context, since it should produce a non-existent universe, makes perfect sense. In this model, the Big Bang represents the ultimate union of existence and non-existence, the whole external universe and its reference frame, the objective and subjective aspects of reality, which otherwise appear to be divided. Given this new possibility that what is unified at the level of the Big Bang could be asymmetrical across time, the pertinent question then becomes, how does the cosmos transition between its matter and antimatter dominant phases? In the context of the present model, we can answer this question straightforwardly. It happens in the same way that the universe transitions between its accelerating and decelerating phases of expansion. To understand why this is the case, recall that when every observable universe expands relative to its observer, every galaxy will diffract into many possible locations in the shared universe. As a result, the configuration of matter itself, on both macro and micro levels, will be completely insubstantial in this universe. On a macro level, any given galaxy, and on a micro level, any given particle, will exist in many possible locations simultaneously. Notice that, in this universe, the halo of possible locations for a galaxy appears directly analogous to the halo of possible locations for an electron. As previously discussed, this universe undergoes a pressure cycle to which every piece of matter on a macro level is responsive. But if we take this model to its logical conclusion, then every piece of matter should also be responsive to this cycle on a micro level. If the configuration of matter itself, on both macro and micro levels, is completely insubstantial, then there is no reason why the pressure cycle of the universe would not also be a cycle of charge. When the balance between attractive and repulsive forces in space on a macro level, pressure, reverses, the balance between attractive and repulsive forces in space on a micro level, charge, should also reverse. In this conceptual framework, pressure and charge, gravity and electromagnetism, therefore appear to be one and the same phenomenon, manifested at different levels of existence. Again, when the expansion of the universe is accelerating, positive pressure is generated around each galaxy in the negative pressure-dominated environment. During this phase, as currently observed, the cosmos is dominated by matter, which is composed of positive charge protons in a negative charge electron environment. As the pressure balance of the cosmos gradually shifts, at some point it finally transitions from an accelerating to a decelerating phase of expansion. And since the balance of pressure switches throughout the entire cosmos all at once, so does the balance of charge. Now negative pressure is generated around each galaxy in the positive pressure-dominated environment. During this phase, the cosmos will be dominated by antimatter, which is composed of negative charge antiprotons in a positive charge positron environment. Finally, notice how this model actualizes a basic principle in the study of physics, that all physical processes should be perfectly reversible. In reality, the physical laws of the universe appear to be unaffected when charge, parity, and time, CPT, are simultaneously reversed, but not when only one or two of the three are reversed. If CPT symmetry is a fundamental property of the universe, but any other combination of C, P, and T symmetry is not, then this principle likely reflects an actual condition in nature, in which case, the fact that the universe is matter-dominant when its expansion accelerates implies that antimatter will dominate when its expansion decelerates, like we just saw. In short, this model predicts a harmonious switching of forces in the universe every kalpa. Again, the red and purple lines in this diagram represent the interplay between the positive and negative pressure components in space, which is reflected by the alternating phases of matter over time. The Flatness Problem. In our standard models of physics and cosmology, there are effectively limitless ways for the cosmos to have either an open geometry, expanding forever, or a closed geometry, recollapsing, but only one way for it to have a flat geometry. A flat universe perfectly balances the relationship between space and matter. It represents the razor's edge between a universe that expands and a universe that contracts. A flat universe will stop expanding after an infinite amount of time. According to our most precise observations, the geometry of the universe appears to be flat, and the cosmic inflation hypothesis is partly justified as a way to explain this incredible coincidence. Under this hypothesis, the universe experienced an early moment of inconceivable expansion, growing from the size of this period to bigger than the currently observable universe in far less than a second. As a result, the initial curvature of the universe, whatever it actually was, got stretched out to the point that it looks essentially flat from any given perspective. Of course, no physical process capable of generating such inflation is currently known. Given the extreme measures that scientists have taken to resolve the flatness problem, it is worth reconsidering from a higher perspective why the flat universe is a problem to begin with. As we know, in the context of general relativity, masses affect the curvature of spacetime. The scientific community therefore infers that the total amount of matter in the universe will affect the curvature of the universe itself. In other words, scientists today directly apply the logic of general relativity, which works in 3 spatial dimensions, onto a hypothetical 4th spatial dimension, a curve in the universe itself, presuming that this logic will be equally as valid on a higher level of analysis. However, as I showed at the beginning of this argument, this is not the case. To see why, consider again what it means to say that the entire universe has a shape. The whole universe can only have a shape, in any real sense, relative to some other reference frame. But our standard picture of the universe does not account for any reference frame relative to which the shape of the universe takes its form. In this picture, the shape of the universe appears as a mysterious end of all inquiry. It plays the role of an absolute ground on which reality itself is manifested. In short, our standard models of physics and cosmology position reality itself as a category within shape. However, in actuality, to state the completely obvious, shape is a category within reality itself. To put it simply, the flatness problem stems from an erroneous attempt to describe reality itself in terms of geometry. In the context of the present model, on the other hand, the apparent flatness of the universe conforms to another perspective entirely, that reality itself does not exist within a higher level shape or a higher level time. Instead, the whole external universe, space-time, and its reference frame, the non-spatial, non-temporal aspect of reality, exist in a reciprocal relationship with each other. In this view, a flat cosmos is just a cosmos that unfolds on the backdrop of non-existence. The essential point is that a fantastic coincidence in the context of general relativity is no coincidence at all from this perspective. In this model, a flat universe is simply not a problem. The Horizon Problem. Our standard models of physics and cosmology struggle to explain why the temperature of the universe, at the largest scales, is almost completely homogeneous. In the context of general relativity, information exchange, such as hot and cold regions of space mixing together to achieve an equilibrium, does not occur faster than the speed of light. 2 regions of space are therefore viewed as causally disconnected if their horizon distances have never overlapped, if the light from one location hasn't had time to reach the other. Under this conceptual framework, our observable universe should be divided into many causally disconnected regions of space, each evolving independently of one another, which raises the question of why the physical conditions of our whole observable universe are so unvarying. In response to this horizon problem, the scientific community has gathered around 2 basic explanations. First, the cosmic inflation hypothesis, which effectively solidifies the shared physical conditions of the early universe. An early flash of rapid expansion would inflate small, homogeneous regions of space to such enormous proportions that once the inflation ended, our whole observable universe would share the same physical conditions of that small region of space from which it was inflated. At that point, the temperature of our whole observable universe would be effectively locked in place. Our own massive region of the cosmos would be causally disconnected from other faraway regions of space, which would evolve independently under different physical conditions, such as temperature. The second, less conventional explanation is that the speed of light is variable across time. If the speed of light was greater in the early universe than it is today, it would allow the cosmos to rapidly mix together to produce the temperature equilibrium that we observe. In the context of the present model, rather than an arbitrary instant of inflation or an arbitrary change in the speed of light, the physical conditions of the cosmos are homogeneous as a result of personal universes coexisting in the shared universe. In other words, the resolution of the horizon problem is intrinsic to the fundamental structure of this theory. To see why, let's review the situation of the black galaxy. In this diagram, light from the Big Bang has traveled across space-time to reach the observers in this galaxy at their unique location in the cosmos. However, as time passes, the black galaxy diffracts into many possible locations in the shared universe, represented by the shaded circle. In this model, each possible location of the black galaxy corresponds to an observer's personal universe, an entire history of space-time in which light from the Big Bang has traveled across the cosmos to reach the black galaxy at that particular location. Since each personal universe, each unique history of space-time, unfolds simultaneously in the shared universe, this entire shaded area of the cosmos represents a region of instantaneous information exchange between different personal universes coexisting in the shared universe. Now let's consider the situations of the blue, black, and green galaxies all at once. Again, each shaded circle represents the many possible locations of each respective galaxy. In this diagram, the blue and green regions of the cosmos are never in direct contact. However, the black region interacts with both of them simultaneously. As a result, the different physical conditions of the blue and green regions adapt to each other through the instantaneous conduit of the black region. To summarize, in general relativity, information exchange occurs between objects within space-time. In the present model, on the other hand, information exchange occurs between entire histories of space-time. While objects within space-time exchange information at the speed of light, entire histories of space-time exchange information instantaneously through the non-spatial, non-temporal aspect of reality, the shared present outside of space-time itself. The essential point is that, in this model, the balance of temperature is coordinated across the entire cosmos in the same way as the balance of pressure and the balance of charge, through personal universes coexisting in the shared universe. Lastly, note that the horizon problem and the flatness problem are the two primary justifications for the cosmic inflation hypothesis. It therefore seems that once these problems are resolved within a more comprehensive theory, the idea of cosmic inflation should be regarded as an extreme solution to a puzzle that no longer exists. The axis of evil. The temperature of the cosmic microwave background, CMB, the earliest visible light in the universe, emitted roughly 380,000 years after the Big Bang, is nearly uniform across the sky at 2.73 degrees Celsius above absolute zero. Here is a simulated image of the CMB as it first appeared to our most advanced instruments in 1965, with light from the Milky Way in the foreground. As telescopes improved, scientists were able to measure the CMB with more precision to reveal its anisotropies, small patches of sky where the temperature varies slightly above or below 2.73 Kelvin. Quote, "These variations in the sea of radiation are small, about 1 part in 100,000, or equivalent to the roughness of dust on a billiard ball's surface." Unquote. After the WMAP telescope returned this data in 2003, scientists began to organize the scattered temperature variations in the CMB into more fundamental patterns of warm and cool regions, called multipoles, which might reveal something about the underlying patterns in nature that generated the CMB's complexity. The simplest multipole is the monopole, which corresponds to the CMB's average temperature of 2.73 Kelvin. The next highest multipole is the dipole, which describes the overall direction in which the CMB is warmer or cooler, and by how much. Next is the quadrupole, then the octupole, etc. Using this technique, scientists uncovered some anomalous patterns in the CMB. In particular, the CMB's large-scale features appear to be aligned with the orientation of our solar system. The ecliptic plane, the plane on which Earth orbits around the Sun, quote, lies precisely between the warmest and coolest lobes of the combined quadrupole plus octupole map, unquote. Scientists then determined that, quote, the likelihood of these alignments happening by chance is less than 0.1%, unquote. This unexplained alignment between the CMB and our solar system, highlighted in this image, was dubbed the axis of evil. Here's another way to look at it. When the CMB is projected onto a sphere, the ecliptic plane is oriented parallel to the divide between the largest warm and cool regions of the universe. This implies, in contrast to our standard models of physics and cosmology, that our solar system is in some small sense at the center of the universe. The sense in which we appear to be at the center of the universe is small because the warm and cool regions of the cosmos that our solar system bisects are almost indiscernibly warm and cool in relation to the average temperature of the cosmos. In short, the axis of evil implies that we are both at the center of the universe and that this position is about as significant as the dust on a billiard ball's surface. To understand this alignment between the ancient temperature map of the cosmos and the plane of Earth's orbit around the Sun, let's consider how the axis of evil fits within the basic conceptual framework of this model. To begin with, let's imagine our personal universe at a higher resolution, with Earth at the center of our horizon distance. Now imagine the ecliptic plane in relation to our horizon distance. As the Earth orbits the Sun, it moves horizontally along this plane, but not vertically. In other words, the center of our personal universe slightly wobbles left and right along the ecliptic plane, but not up and down. In principle, this resolves the narrow problem of why the warm and cool regions of the cosmos are divided along the ecliptic plane and not perpendicular to the ecliptic, or any other angle in between. If our whole observable universe wobbles along the x-axis, but not along the y-axis, then its conditions would also mix in this direction, sort of like shaking a plate of sand. In this picture, the cool region above the ecliptic mixes horizontally, but not vertically. Likewise, the warm region below the ecliptic mixes horizontally, but not vertically. In sum, our personal universe achieves an equilibrium in the horizontal direction, but not the vertical. Of course, the broader problem in question is how the small, contemporary orbit of Earth around the Sun creates an imprint on the ancient structure of the entire cosmos. In order to resolve this broader problem, let's reconsider our standard picture of the universe. As we typically understand it, space-time is conceived as the most fundamental aspect of reality, which is another way of saying that reality is defined as an area. In this picture, the external universe has some unknown absolute size, within which the big things are composed of the small things in the normal way, like building blocks. The small things we see through a microscope permeate the big things we see through a telescope. In the present model, on the other hand, two fundamental aspects of reality are conceived in a relationship with each other: the objective aspect, the whole external universe, and the subjective aspect, the reference frame for the universe itself. As a result, the universe has no absolute size of its own. The size of the universe can only be measured relative to the observer. In this context, it is incorrect to say that the small things we see through a microscope permeate the big things we see through a telescope. Instead, the extreme microscopic level of reality and the extreme macroscopic level of reality are related to each other only insofar as they both exist at the extreme edges of our perception. In short, if we take this model to its logical conclusion, then the scale of the universe must be defined in orders of magnitude away from the observer. With this in mind, consider that when a person looks into space, the limits of their vision appear to be precisely the same whether they look in through a microscope or out through a telescope, as measured from the smallest thing visible to the naked eye. We can theoretically peer 10 to the minus 31 meters through a microscope, at which point we would reach the Planck length and see the quantum foam at the base of all reality. And we can theoretically peer 10 to the 31 meters through a telescope, at which point we would see the first light from the Big Bang at the base of all reality. To state the obvious, this is precisely what we would expect to find if subjectivity, here and now, was a reference frame for the universe itself. Of course, when we look through a telescope, we assume that we are looking back in time. However, when we look through a microscope, we assume that we are not. But why should lenses with long focal lengths enable a person to see through time, while lenses with short focal lengths do not? If the universe has no absolute size of its own, but can only be measured relative to the observer, then the basis for this asymmetry unravels. If 10 to the minus 31 meters is the same distance as 10 to the 31 meters, then there is no reason why looking far into space with a telescope would enable a person to see through time, while looking far into space with a microscope would not. If we take this model to its logical conclusion, then the extreme microscopic level of reality and the extreme macroscopic level of reality are equivalent, and the evolution of the cosmos must be viewed as a process that occurs in two directions simultaneously, on either side of the observer. Let's reconsider the CMB in this new context, where the base of all reality can be found at the extreme ends of our perception, through a telescope and a microscope equally. In order to visualize this effectively, let's pretend that particles created by the Big Bang travel in two directions simultaneously, down from 10 to the 31 meters to the Earth, and up from 10 to the minus 31 meters to the Earth. In short, let's pretend that there are two CMBs, one macro and one micro, with observers on Earth bisecting the two precisely. In this diagram, the axis of evil is essentially self-explanatory. The scale of the ecliptic plane is negligible as particles travel down from the macro CMB. But as those same particles travel up from the micro CMB, the ancient structure of the cosmos evolves into the enormous contemporary orbit of Earth around the Sun. This mixes the entire cosmos left and right, along the ecliptic plane, but not up and down. Since both CMBs are actually one and the same, we can see the imprint of our solar system spread across the vista of the oldest light in the universe. Contrary to our standard picture of the universe, this model implies that at the extreme microscopic level of reality, it is still a split second after the Big Bang. As a particle makes its journey through time, it diffracts into possible histories, forms possible bonds with other particles, and finally ends up in possible Earths. Of course, this model also implies that the CMB will look different to observers on different planets, at the center of different personal universes, but this difference will be about as significant as the dust on a billiard ball's surface. This equivalence between the extreme microscopic and the extreme macroscopic levels of reality also means there is a fractal quality to the cosmos. We could zoom through our personal universe forever in both directions, in through a microscope and then out through a telescope. Big Bang, Earth, Big Bang, Earth, etc. In this picture, we can imagine the non-spatial, non-temporal aspect of reality, the reference frame for the universe itself, existing at the singularity that connects the extreme microscopic and the extreme macroscopic levels of reality. At a higher resolution, we can imagine this dimensionless dimension seated equally at the microscopic and the macroscopic edges of existence. In summary, if subjectivity here and now is a reference frame for the universe itself, then the cosmos must be visualized as a multitude of personal universes coexisting in the shared universe. In this picture, each personal universe is an entire history of space-time that evolves from the base of all reality at the micro and macro levels simultaneously and converges on the observer. The arrow of time. As previously discussed, it is a fundamental proposition in the study of physics that all physical processes should be perfectly reversible. There should be a symmetry of physical laws given the simultaneous reversal of charge, parity, and time. However, in our standard picture of the universe, this anticipated symmetry only holds true at the micro level. At the macro level, both charge and parity, the spatial coordinates of a physical process, seem perfectly reversible, but the arrow of time does not. The irreversibility of time on a macro level is noticeable when we fry but cannot unfry an egg, to use a typical example. The egg can only move in one direction, from an ordered, low-entropy state to a disordered, high-entropy state. This characteristic of nature is formalized in the second law of thermodynamics, which states that the total entropy of a closed system must always either remain constant or increase over time. Accordingly, if the entire universe is pictured as a closed system, then its entropy will always tend to increase, and eventually, the cosmos will exhaust itself into a disordered realm of inert, empty space. From a physics perspective, the essential point is that the direction of time itself, whether time flows forward or backward, appears to be best defined by whether the overall entropy of the universe is increasing or decreasing. This relationship between entropy and the arrow of time raises two basic problems for the studies of physics and cosmology. Why does time appear to be reversible on a micro level but irreversible on a macro level? And why is the universe currently in a highly ordered, low-entropy state? To resolve these problems, our standard picture of the universe imagines that the cosmos began, for some unknown reason, in a state of extremely low entropy. According to this view, the highly ordered universe that we find today, full of galaxies and planets, is simply a function of our proximity to the beginning of time. Moreover, the fact that the physics of matter is time reversible on a micro level but irreversible on a macro level is simply a consequence of nature's unexplained preference to begin in a state of extremely low entropy and to end in a state of extremely high entropy. In short, our standard explanation for the arrow of time amounts to little more than that's just the way it is. In contrast, let's consider the arrow of time in the context of the present model. As previously implied, the arrow of time effectively points in two directions at once, on either side of the observer. Now let's take this diagram and apply it to the different phases of our intracyclic model of cosmology, starting with the accelerating phase of expansion. When particles accelerate down from 10 to the 31 meters to the Earth, they also evolve and complexify up from 10 to the minus 31 meters to the Earth. Remember that in this conceptual framework, these two directions of cosmic evolution, down from a macro level and up from a micro level, are actually one and the same. During this phase, everywhere that we look, whether in through a microscope or out through a telescope, is back in time. In short, when the expansion of the universe accelerates, time flows forward and entropy decreases. On the other hand, when the expansion of the universe decelerates back up toward 10 to the 31 meters from the Earth, physical structures in the universe devolve and decomplexify back down toward 10 to the minus 31 meters from the Earth. Again, in this conceptual framework, these two directions are one and the same. During this phase, everywhere that we look, whether in through a microscope or out through a telescope, would be forward in time. In short, when the expansion of the universe decelerates, time flows backward and entropy increases. Notice how this intracyclic model of cosmology reflects what was already implied by the Hindu system of alternating kalpas. A universe that undergoes regular cycles of increasing and decreasing entropy will be a universe with a regular life cycle. In this universe, like a field full of flowers that all blossom and perish according to the seasons, the life-producing ability of every galaxy will be responsive to the changes in our common cosmic seasons. Furthermore, recall that when the expansion of the universe was decelerating, the halo of possible locations for any given galaxy, depending on the observer, had a diameter that was shorter than the cosmic horizon distance. Then, when the expansion of the universe accelerated, the diameter of this halo surpassed the cosmic horizon distance, and the possible locations for any given galaxy crossed beyond the edge of all reality. In the present context, notice how the universe looks like a closed system in its decelerating phase of expansion. In a closed system, the second law of thermodynamics holds true, meaning that the total entropy of the universe should increase over time, like we just saw. On the other hand, the universe appears to be an open system in its accelerating phase of expansion. In an open system, the second law of thermodynamics is inapplicable, meaning that the total entropy of the universe should decrease over time, again, like we just saw. In this conceptual framework, both inside and outside the universe are accounted for as fundamental aspects of reality in their own right. Metaphorically speaking, in this intracyclic model of cosmology, it is as though space-time itself was continuously revitalized by the non-spatial, non-temporal aspect of reality. Empty yet inexhaustible, used but never used up. It is like an eternal wellspring that gives birth to infinite worlds. In summary, this model accords with our intuitive proposition about the study of physics, that all physical processes should be time-reversible on both micro and macro levels. Again, there is a harmonious switching of forces in the universe every kalpa. The red and purple lines represent the interplay between the positive and negative pressure components in space, which is reflected by the alternating phases of matter, time, and entropy. Dark flow. In 2008, a group of scientists discovered some unexpected motion in a large collection of galaxy clusters. The clusters appeared to be drifting toward the edge of our observable universe. They dubbed the motion dark flow. In their first report, the scientists determined that, quote, this motion is constant out to at least 1 billion light-years, unquote. In their second report, a year later, they updated their analysis, finding that 1,400 galaxy clusters are part of a flow that stretches twice the distance originally reported, to 2.5 billion light-years. Their working assumption is that, quote, because the dark flow already extends so far, it likely extends across the visible universe, unquote. Subsequently, the discovery team sorted their data into 4 slices of distance ranges. When they examined the flow within each slice, they found that, quote, the overall trends among the slices exhibit remarkable agreement, unquote. In other words, quote, the clusters show a small but measurable velocity that is independent of the universe's expansion and does not change as distances increase, unquote. The clusters appear to be moving nearly 2 million miles per hour, or about 900 kilometers per second, along an imaginary line that extends from Earth toward the constellations Centaurus and Hydra. However, the direction of the flow itself is less certain. Quote, we detect motion along this axis, but right now our data cannot state as strongly as we'd like whether the clusters are coming or going, unquote. The leading explanation for dark flow is that the galaxy clusters are being drawn towards something beyond the edge of our observable universe. The existence of dark flow, quote, suggests that some structure beyond the visible universe, outside our horizon, is pulling on matter in our vicinity, unquote. In the context of our standard models of physics and cosmology, this flow could only have originated shortly after the Big Bang, when regions of the cosmos that are currently beyond our horizon distance were close together, and therefore able to be gravitationally affected by each other. In other words, dark flow must be a relic of old gravitational interactions. It can have no contemporary cause. The essential point is that dark flow is anomalous in the context of our standard models of the universe. In a universe that expands relative to itself, or doesn't expand relative to anything, there should be no flow of matter in any preferred direction at very large scales. However, in a universe that expands relative to the observer, dark flow is an unsurprising phenomenon. To see why, let's first consider how the present model relates to Hubble's law. Hubble discovered that galaxies recede away from us with a velocity that is proportional to their distance. More distant galaxies move faster than nearby ones. His observations indicate a constant expansion throughout the universe. All galaxies recede away from each other at a constant speed per unit of distance. In the present model, Hubble's law is reflected in the shared universe. It is explained by the fact that the universe expands relative to every observer in every galaxy. To briefly illustrate this point, here are 5 galaxies, all equal distances away from each other, before and after expansion. From the perspective of observers in the black galaxy, the blue galaxy receded 1 unit of distance in 1 unit of time, while the red galaxy receded 4 units of distance in 1 unit of time. There is a compounding effect in the recession of galaxies over large distances, which is produced by the constant expansion of space between each galaxy. Of course, the same thing is true in the opposite direction and in every other direction as well. But Hubble's law is not reflected at the level of personal universes, which only expand relative to their one observer. The observer in the black galaxy sees every other galaxy recede 1 unit of distance in 1 unit of time. There is no compounding effect in the recession of galaxies over large distances. Since the observer in the black galaxy is the only observer in their universe, there is no other point of reference relative to which their personal universe could expand. As previously discussed, this generates a problem in the shared universe, an incongruity in the location of galaxies depending on the observer. And this problem is resolved by the diffraction of galaxies into many possible locations. After 1 unit of time, every galaxy in the universe diffracts 1 unit of distance in every direction. After 2 units of time, every galaxy has diffracted 2 units of distance away from its original location. After 3 units of time, 3 units of distance, and so forth. If we return to the perspective of any one observer at the center of their personal universe, location 0, the whole cosmos appears to shift away at a constant rate, which is precisely what the Discovery team found in dark flow. Of course, dark flow has only been detected in the direction of the constellations Centaurus and Hydra, but in the future, when scientists measure other massive groups of galaxy clusters, this phenomenon should be detected along every line of sight between Earth and the horizon of our visible universe. In order to understand how Hubble's law is both reflected and not reflected in the expansion behavior of the universe, let's combine the two perspectives, personal universes coexisting in the shared universe. Again, here are 5 galaxies, all equal distances away from each other, before and after expansion in the shared universe, obeying Hubble's law. At the same time, observers in these 5 galaxies each have personal universes that expand relative to them alone. For the sake of clarity, let's look at what happened to the red galaxy. After 1 unit of time, the red galaxy exists in 4 different locations, depending on the observer. From the perspective of observers in the black galaxy, the red galaxy began 4 units of distance away. After 1 unit of time, the red galaxy diffracted into 4 possible locations. It is either 5, 6, 7, or 8 units of distance away. At this point, recall that the direction of dark flow was difficult for scientists to establish. Evidence indicates that the clusters are flowing away from Earth, but the team could not rule out a flow in the opposite direction. From this vantage point, is the red galaxy flowing away from observers in the black galaxy, from distance 5 to distance 8? Or is it flowing towards the black galaxy, from distance 8 to distance 5? Here's another way to think about it. In this diagram, the purple galaxy represents all observers who exist on the same line of sight relative to the red galaxy. As the universe expands, all observers who are on this line of sight see the red galaxy recede in the same direction. However, from the perspective of any one observer, the red galaxy has diffracted into many possible locations on this waveline. As a rule, once we determine the velocity of the red galaxy, the line on which it recedes, we necessarily become uncertain about its position. To know the velocity of the red galaxy in our personal universe is to be uncertain of its position in the shared universe. On the other hand, once we determine the position of the red galaxy, we necessarily become uncertain about its velocity. The red galaxy could be receding along any line of sight in any direction, depending on the observer. To know the position of the red galaxy in our personal universe is to be uncertain of its velocity in the shared universe. The function of the uncertainty principle is to prevent any one observer from violating another observer's reality. If the red galaxy's position and velocity were both solidified from one perspective, it would violate someone else's perspective in the shared universe. As a result, our knowledge about the red galaxy's full existence is inherently limited. From our perspective, there appears to be only one red galaxy, but in the shared universe, the red galaxy is diffracted into many versions of itself, all of which are simultaneously real as possibilities. In this conceptual framework, notice how the wave-particle duality only becomes apparent at extremely large and extremely small scales. In order for an object to diffract into many possible locations in the shared universe, become a wave, it must be sufficiently distant, in orders of magnitude, from its various observers, who each observe the common object from their own personal universes. If the object is nearby, then it has no reason to diffract. Its one location is close enough to subsume the minor differences between the perspectives of its various observers. With this in mind, we might ask, at what distance do cosmic objects begin to diffract into many possible locations relative to observers in different galaxies? Given our current knowledge about dark flow, we can answer this question straightforwardly. The speed of dark flow, the constant rate at which the cosmos appears to shift away from our perspective, relative to the expansion rate of the universe, reveals the distance at which a cosmic object begins to diffract into a wave. 900 kilometers per second divided by 73.5 kilometers per second per megaparsec equals 12.245 megaparsecs, or 39.92 million light-years. Galaxies begin to diffract into different possible locations in the shared universe at a distance of about 40 million light-years from an observer. For a sense of scale, our local group of galaxies, to which the Milky Way belongs, has a diameter of about 10 million light-years. For an additional sense of scale, let's compare this wave-particle duality on macro and micro levels. According to this calculation, a galaxy begins to diffract into different versions of itself at about 10 to the 23 meters from an observer. In comparison, on the micro level, 10 to the minus 23 meters is roughly the scale of quarks and neutrinos. In response to the dark flow study, which was based on an analysis of the cosmic microwave background, another group of scientists decided to measure the flow of galaxies using a different data set, a catalog of type 1a supernova. This team measured the collective motion of galaxies on a smaller scale, an imaginary sphere with a radius of about 240 million light-years. Within that area, they detected a flow of 250 kilometers per second, roughly 4 times slower than the original dark flow measurements. In principle, this slower motion could be explained as a consequence of the normal gravitational pull of other galaxies. It is therefore potentially consistent with our standard models of physics and cosmology. The results of this follow-up study prompted some scientists to conclude that the original dark flow team must have massively underestimated the error bars in their analysis, and that dark flow doesn't exist. There are basically 2 ways to reconcile these conflicting studies of dark flow. 1. The original dark flow study was inaccurate, dark flow doesn't exist, and the follow-up study simply measured the normal gravitational pull of galaxies in the cosmos. Or 2, the original dark flow study was correct, and the follow-up study reveals an additional aspect of the same dark flow phenomenon. Regarding the second possibility, the leader of the follow-up study visualized what it would mean for the results of both studies to be accurate. Quote, "Consider a boat, a really big boat. The dark flow discovery team measured the motion of the boat, the collective bulk of galaxy clusters speeding across the ocean. Meanwhile, with the supernova data, I'm measuring the motion of a person. Now, that person is on the boat, and the boat is moving, but that's going to give us some additional motion inside the boat. If the person is not sitting down but running inside the boat, then both motions could be happening simultaneously, and the two results could be reconcilable." Unquote. In the context of the present model, the boat metaphor is clearly pertinent. The follow-up team detected a flow of roughly 250 kilometers per second, which is the speed of the person who is running inside the boat. Given this figure, we can calculate the distance at which the person inside the boat begins to run relative to the expansion rate of the universe. Or, another way to think about it is the size of the person who is running inside the boat. 250 kilometers per second divided by 73.5 kilometers per second per megaparsec equals 3.4 megaparsecs, or 11 million light-years, roughly the size of our local group of galaxies. In short, the original dark flow study measured a boat of galaxy clusters flowing across the universe, while the follow-up study measured a person, our local group of galaxies, running inside the boat. In the terms of this model, the original dark flow study measured the diffraction of cosmic objects across the universe, while the follow-up study measured the size of the cosmic objects that get diffracted. Now let's reconsider a previous diagram. From the perspective of observers in the black galaxy, the red galaxy began 4 units of distance away. After the universe expanded for 1 unit of time, we saw the red galaxy diffract into 4 possible locations. But the black galaxy itself will also diffract 1 unit of distance in 1 unit of time. As a result, notice how the black galaxy must return to the location of its own observers at the center of their personal universe, location 0. In this picture, not only is the speed of the boat, the red galaxy, faster than the speed of the person, the black galaxy, but the two flows are in opposite directions, which is precisely what the follow-up team discovered when they compared their results to the original dark flow measurements. The boat in the original dark flow study is speeding away from Earth, while the person in the follow-up study is running towards us. Finally, notice how the dual motion of dark flow mirrors the interplay between dark matter and dark energy. The person running inside the boat, the black galaxy, accords with the force that is exerted back onto the black galaxy from every direction, dark matter, while the flow of the boat, the red galaxy, accords with the force that is exerted away from the black galaxy in every direction, dark energy. In summary, dark flow, dark matter, and dark energy are different consequences of the same phenomenon, personal universes coexisting in the shared universe. All 3 are straightforwardly explained in the context of a universe that expands relative to the observer, rather than a universe that expands relative to itself, or doesn't expand relative to anything. The Vacuum Catastrophe. As previously mentioned, if we assume that dark energy is vacuum energy, the pressure component in space itself, then its density must be 120 orders of magnitude lower than what is predicted by quantum field theory. Given the sources of these 2 values for vacuum energy, the first, 10 to the minus 8 ergs per centimeter cubed, as measured in the context of general relativity, and the second, 10 to the 112 ergs per centimeter cubed, as predicted in the context of quantum field theory, the scientific community is, at present, fundamentally unable to explain this vast discrepancy. However, in the context of the present model, this vacuum catastrophe is straightforwardly explained as the result of personal universes coexisting in the shared universe. At the level of an observer's personal universe, only a single version of any given particle is manifested. But in the shared universe, every particle is diffracted into many versions of itself, all of which are simultaneously real as possibilities. Therefore, from our direct perspective, only a small amount of energy is present in the vacuum of our universe. But from a God's eye point of view, in the shared universe, there is a huge amount of vacuum energy. Every possible location of every particle is simultaneously real in the sum of all spacetimes. In short, the lower value for vacuum energy, as measured in the context of general relativity, reflects the energy in the vacuum of our personal universe, while the higher value, as predicted in the context of quantum field theory, reflects the energy in the vacuum of the shared universe. This higher value is never manifested in any given observer's personal universe, so each personal universe gradually expands according to its own minuscule pressure content. The vacuum catastrophe does not represent a failure in the equations of quantum mechanics or general relativity. Instead, it represents an even more basic failure in our theoretical picture of reality, a failure to explicitly account for the reference frame relative to which the universe expands. The essential insight needed to unite our two models of physics is to realize that subjectivity here and now is the context in which the whole external universe is manifested. Once a scientist opens this inconceivable door, it is a short time to see how the vacuum catastrophe, along with the other major problems of modern physics, can be resolved within a single theoretical framework, where the objective and subjective aspects of reality, the whole external universe and its reference frame, are conceived in a reciprocal relationship with each other, where space-time itself is quantized relative to the observer. Review. When space-time is defined as the most fundamental aspect of reality, when reality itself is defined as an area, the only way to explain consciousness is to say that it emerges out of certain points in space at certain points in time. Within the framework of space-time, this is the only available explanation for consciousness, which is undeniably real and therefore has to be explained. But consciousness itself, the realm of experience, is not a space-time object, so the idea that it emerges out of complex space-time objects seems logically discontinuous within the framework of space-time. To put it simply, no one knows what an emergent subjectivity even means. It is a popular concept only because it is a necessary addendum to the theory of space-time. Space-time cannot be defined as the most fundamental aspect of reality without creating further addendums to the theory. As I showed at the beginning of this argument, the theory of space-time relies upon the concepts of infinite space or a fourth spatial dimension for its tentative coherence. In total, the modern cosmological paradigm is propped up at its foundation by at least 8 disconnected major concepts: infinite space, a fourth spatial dimension, dark energy as a cosmological constant, dark matter as a particle, a decisive structural difference between matter and antimatter, cosmic inflation, extremely low entropy at the beginning of time, and countless emergent subjectivities. In addition, our standard picture of the universe contains at least 2 outstanding major anomalies: the axis of evil and dark flow. Lastly, and most significantly, the entire branch of quantum physics could be interpreted as an addendum to spacetime. It exposes features of reality that are undeniably real, but in the context of spacetime are lacking a coherent explanation. In this argument, I showed how our major addendums to spacetime are symptoms of a basic failure to integrate the non-spatial, non-temporal aspect of reality into the structure of the theory. The challenge for scientists moving forward is to refine, extend, and articulate this new understanding of spacetime as one of 2 reciprocal aspects of reality: the whole external universe and the reference frame for the universe itself. Part 3. Conclusion. When dark energy was discovered, scientists became fond of calling it the ultimate Copernican revolution. It appears to displace human beings even further from the center of reality. Quote, "Not only are we not at the center of the universe, but we are not even made of the same stuff as most of the universe." Unquote. But revolutions often upend our initial interpretations of them. As much as we are insignificant creatures in the vastness of space, we are also keepers of the universe itself. Reality happens on the divide between the whole external universe and its reference frame. We live on the edge of the universe. We are half inside the universe, half outside of it. We exist at the convergence point between space and the infinite here, time and the eternal now, being and non-being, the objective and subjective aspects of reality. The promise of the coming era is a deeper union between our knowledge and our experience. In this new era, to understand the nature of reality is to realize the essence of the self.